Overflow is one of the oldest problems in data representation. It is also one of the most dangerous because when overflow happens, systems often continue operating as if nothing went wrong. A helpful metaphor for overflow is pouring water into a glass. As long as the water level stays below the rim, everything is fine. The glass represents the limits of representation. But once the glass is full, any additional water does not disappear politely. It spills over, making a mess elsewhere. Overflow works the same way in data systems. So what is overflow? Overflow occurs when a value exceeds the maximum range that a representation can hold. Every numeric representation has bounds. Integers have a fixed number of bits. Counters have limits. Memory addresses have finite size. When a computation produces a value outside those bounds, the system must do something with it. That event is overflow. Overflow is not a loss of precision. It is a violation of representational capacity. How does overflow occur? Overflow usually arises during arithmetic operations. Addition, multiplication, accumulation, and iteration can all push values beyond their allowed range. This often happens silently, especially in low-level systems or performance-critical code. In some systems, overflow wraps around. A value exceeding the maximum jumps back to the minimum. In others, it clamps to the maximum allowed value. Some environments raise explicit errors. Others produce undefined behavior. The same operation can behave very differently depending on language, hardware, and configuration. Overflow can also occur in time. Counters tracking requests, timestamps, or identifiers may overflow after long-running operation, even if individual values seem small. Why do systems allow overflow? Because limits are unavoidable. Representations must be finite to be efficient. Fixed-size integers are fast, predictable, and memory efficient. Removing limits entirely would make systems impractical. Overflow is the cost of choosing bounded representations. In some cases, overflow behavior is intentional. Wraparound arithmetic is useful in hashing, cryptography, and low-level optimizations. But intentional overflow must be carefully designed. Accidental overflow is a defect. Overflow has several defining features. First, it is discontinuous. Small input changes can produce dramatic output changes once a boundary is crossed. Second, overflow often breaks assumptions. Ordering, monotonicity, and proportionality no longer hold. Third, overflow is frequently invisible. Systems may not log it, detect it, or signal it. The data looks valid, but it is wrong. Finally, overflow is context-dependent. The same value may be safe in one representation and catastrophic in another. The implications of overflow are severe. In finance, overflow can corrupt balances and totals. In analytics, it can reverse trends or reset counters. In security, overflow vulnerabilities have been exploited to bypass checks and execute arbitrary code. In distributed systems, overflowed identifiers can cause collisions, data loss, or inconsistent state. In machine learning and scientific computing, overflow leads to infinities, NaNs, and unstable training dynamics. Overflow erodes trust because its effects are often delayed. The system appears correct until a boundary is crossed. Then, failures emerge far from the original cause, making diagnosis difficult. Professional data systems treat overflow as a first-class concern. They choose representations with appropriate ranges. They monitor boundary conditions. They fail loudly rather than silently when overflow occurs. Because overflow is not just a numerical glitch, it is what happens when reality exceeds the container chosen to represent it. And once the value spills over, the original meaning is no longer guaranteed.